Looking at our broad categories of the hydrocarbons, remember we had our one other video talked about alkanes, and an alkane is characterized by all carbon-to-carbon single bonds, which means that those two carbons have to have four other things bonded to them. Alkenes are characterized by a carbon-to-carbon double bond, which means that those two carbons would each have two other things bonded to them. Alkynes, carbon-to-carbon triple bond, which means that each carbon would have one other thing bonded to it. And again, kind of thinking in terms of our VSEPR and valence bond theory, obviously alkynes are going to have linear arrangement of the two carbons. Alkenes would have a trigonal planar with 120-degree bond angles, and alkanes obviously have our three-dimensional tetrahedral arrangements. Aromatics are special molecules that have a benzene ring. Now, a benzene ring is a six-membered carbon ring. So there's 6 carbon atoms around this ring. Now, what makes a benzene ring special is that it has resonance, 2 resonance forms. Okay. And you recall that when we have resonance, what that really means is we have this delocalized pi bond. So let's see if we can take a look at what that delocalized pi bond looks like. So here we have our 6-membered ring, and so you can see that around each carbon we've got our sp2 hybrid orbitals overlapping with the hydrogens to make one bond, and then overlapping with the adjacent carbons, forming those sigma bonds all around. And of course, that angle then here would be 120 degrees, as it's an sp2 hybrid orbital there. Now, what that leaves is the unhybridized p orbitals. So if you're looking at the picture on the top picture on the left here, those unhybridized p orbitals are coming straight out of the board. If we turn that sideways slightly, we can see that we have those unhybridized p orbitals in the image on the right, where they're going directly above and below the plane that contains the 6 carbon atoms and the 6 hydrogen atoms. We then apply the idea of the pi bonding, where there's the overlap on the top and the bottom. But instead of looking at it as a resonance in these, the 2 pictures on the left, A and B, we realize that what's really happening is picture C here, where all of those orbitals are overlapping on the top, above and below the benzene molecule. And you have 6 electrons worth of density then spread out over this entire structure. Now, that's an incredibly stabilizing effect, as it turns out. And so this molecule ends up being involved in many different structures. So as you do your projects, many of you will see this structure pop up in some of your molecules. All right, the naming of these things, the key here is that when you name them, you have to count through the double bond. So you still want to find the longest chain, but you want to number it so that your numbering goes through the double or the triple bond that exists. So for instance, up here, and you want the numbering, again, to be as low as possible. So we'd have a 1, 2, 3, 4, 5. And the double bond starts on the 2nd carbon. So this would be called 2 pentene. Again, that ene ending is the indication that there's a double bond, and the 2 tells you that the double bond starts on the 2nd carbon, so it's between the 2nd and the 3rd. So you'd number it with the lowest carbon. If you look at the one below that, numbering it. Now this time I'm going to end up numbering from the left. So I have 1, 2, 3, 4, 5. So it's still going to be kind of a pentene, but in this case we have 2 double bonds. So we're going to have a 1, 3 pentadiene. All right, so what this is telling us is that there's a double bond that starts on the first carbon, a double bond that starts on the third carbon, and it's a diene. So there's 2 carbon-to-carbon double bonds. So again, the double bond starts on the first carbon and the third carbon. So we get that 1,3 pentadiene. If I look at this one here, again, if we watch are careful with our misconceptions here, we want to number it with the double bond having as low a number as possible. So we want to start from the left. So we're going to go 1, 2, 3, 4. And all we want to do here is just take a moment to consider, do we want a number going up or do we want to keep going to the left? Well, if we number going up, there's 3 more carbons, and to the left there's only 2 more. So we actually want to go up here. So 5, 6, and 7. So we would have our double bond. Our double bond starts on the second carbon, and then we have this group here with 2 carbons, so it would be an ethyl group on the fourth carbon. So naming this, we would say it is a 4-ethyl, right, the ethyl group, 2, let's see, 7 carbons, so 2-heptene. Again, that ENE showing that there's a double bond, and the 2 because it's on the second carbon, and the 4 for the ethyl. So 4-ethyl, 2-heptene. Notice I use dashes to separate the numbers from the letters. Okay, this one again, it just becomes kind of a numbering nightmare here. If we try to number the double bond as low as possible, we want to start over on the right. So we do 1, 2, 3, 4. Now at that fourth one, we've got 3 different ways that we could go. We could go up, left, or down. And obviously down has the most carbons, so we'll go 4, 5, 6, 7, 8, and 9. So we have a double bond at the second carbon. We have an ethyl group at the fourth carbon, 2 carbons. And we have a propyl group also at the fourth carbon. So remember, we go by alphabetical. So eth is going to go before prop. So we would say 4-ethyl, 4-propyl, and then our double bond is on the second, 2, and we have 9, so it would be nonene. Kind of an awkward name there, but so 4-ethyl, 4-propyl, 2-nonene. So again, showing that there's a double bond starting with the second carbon of 9. Now, the benzene ring, naming of this, there's 2 different naming conventions that we can use. One is just a straight numbering convention. So I'll show that in green. So if we look at the first one here, this would be methylbenzene. And what we would do here is number things starting with the relative position. So we would call that position 1. This would be position 2, position 3, position 4, position 5, and position 6. So if we were to add something else onto here, like perhaps a chlorine, we could say it would be a 1-methyl, 2-chloro, I guess we should do it alphabetically, 2-chloro, 1-methyl benzene. So that would be one option. The other way that we can name things is by a system called, where the second position is the ortho position. and the third position is the meta position, and the fourth position is the para position. So ortho, meta, para. And then if you were to look at positions 5 and 6, they would have the same name. So position 5 would also be a meta position because it's 2 away from the top one, and position 6 would be an ortho position. So given that, the one next over here, if we use a numbering system, it would be a 1, 2. So we would have 1, 2 dimethylbenzene. So 1, 2 dimethylbenzene. Or we could call it ortho dimethylbenzene, or just O for short, ortho dimethylbenzene. Showing that if we put the one methyl group at the top, the second one's ortho to it, which would mean the carbon directly next to it. So either one of those two names would be appropriate. And likewise, if we go to the next one, this would be a 1, 3 dimethylbenzene, or that'd be the meta, so meta dichlorobenzene. And then finally, the last one, if we put the methyl on the opposite side, we would have a 1, 4 dimethylbenzene, or we could call it para dimethylbenzene. Okay. So we should be familiar with both of those naming conventions for the benzene ring. So this will conclude our discussion of just strictly hydrocarbons. Our next talk will get into some of the functional groups. So once we add other elements into the molecules, we can create some more versatility in the molecules, which obviously is something that's needed for the diversity inside of all living organisms.